I'm Hajime Kawai from R&D department at Nippon Shokubai. I'm from Japan. Today, I'd like to talk about our superabsorbent polymer technology for concrete. First of all, let me introduce our company briefly. Nippon Shokubai was the first company in the world to commercialize PC superprocessor in 1980s under the brand name Aquarock. Our Aquarock polymers are used widely for the production of good concrete, high quality concrete. Actually, we have been a global manufacturer of superabsorbent polymer, supplying mainly the products for hygiene, diapers, and so on. As you know, the reduction of carbon dioxide emissions is an essential issue for the cement and concrete industries. To contribute to the realization of sustainable societies, we have been recently developing various technology for sustainability, such as less clinker, durability, 3D concrete printing, and carbonations. As part of our activities, we are focusing on superabsorbent polymer for concrete, expecting utilizing our knowledge of cementitious and SAP. Numerous studies have indicated SAP can provide multiple benefits on concrete properties. After mixing, SAP can absorb a lot of water, as much as 10 times of their own weight. And as relative humidity in concrete decreases, SAP releases water and cement hydration get promoted accordingly. Strength and shrinkage of concrete are improved, which is referred as internal cooling effect. Furthermore, air voids created by SAP can enhance freeze-thaw resistance of concrete, acting as substitute for entering air. And SAP also show self-cracking healing effect through re-swearing. Despite these advantages of SAP, the widespread use of SAP in concrete has not yet been realized. We will explore the reasons behind this. When conventional SAPs are added to fresh concrete, the probability of fresh concrete is significantly reduced, declined, because conventional SAP absorb a lot of water quickly. To reduce the impact, if extra water is used, of course, it is impossible to improve good physical properties of concrete. We think these concerns would cause the limited practical use of SAP in concrete field. We've expected the SAP which have slower absorbing behavior would be able to achieve both good handling and good physical properties. Therefore, it is crucial to develop SAPs that have slow absorbing behavior. And how is the slower absorbing behavior achieved? In the next slide, I'll explain about our new design for slow absorbing SAP. This slide presents our new design of cross-linked structure of SAP for slow absorption. Conventional SAP, which is based on acid salt monomers, can absorb a lot of water quickly due to osmotic pressure and static pressure. It raised the flowability issues, as I mentioned earlier. To address this, we've developed a new design new design concept that incorporate non-unique groups and stimuli-responsive units into the SAP structure. By replacing acid salt groups by non-unique groups, we can weaken osmotic pressure and eliminate static pressure, allowing for a gradual absorption. Furthermore, the combination of non-unique groups and stimuli-responsive units enables the SAP to increase absorbing rate. As these responsive units gradually creeped in concrete. This innovative approach is expected to enhance the internal curing effect by supplying water to the cement as relative humidity decreases. This slide presents absorption behavior of new SAP in synthetic cement pore solution. This graph shows the relationship between time and the amount of water absorbed by different type of SAP. We have 3 examples of new SAP based on our new concept. New SAP 1, which contains only non-unique groups. On the other hand, new SAP 2 and 3, which incorporate non-unique groups and stimuli-responsive unit. As shown in this graph, the initial absorption amount of new SAPs are lower than conventional SAP. And this data shows the effectiveness of our new design. And notably, our new SAPs, our new SAP 2 and 3 shows faster absorbing behavior compared to new SAP 1 due to this responsive units gradually creeped. This new design allows us to achieve a wide range through absorption behavior by adjusting the proportions of non-unique groups and stimuli-responsive units. This slide highlights the impact of SAP on flowability of fresh concrete. In our concrete test mix design, water cement ratio was 0.45, and we used 1.15 kg of SAP per cubic meter concrete. We compared initial slump at the same dosage of PCE. This graph clearly indicates while conventional SAP affect significantly on flowability on initial swamp, but degrees in swamp were much less when using new SAPs. And this data shows effectiveness of our new design for superabsorbing behavior, and minimize the negative impact on flowability. And we observed swamp retention behavior varies depending on the absorption rate and amount of new SAPs. This slide highlights the impact of our new SAPs on the compressive strength. We compared the compressive strength after 28 days. When conventional SAP was used along with extra water, there was a significant decrease of compressive strength in strength. In contrast, our new SAPs show strength enhancement compared to control mix without any SAP. And so, this data shows relationship strength, increase in strength and between increase in strength and absorption amount of new SAPs. So this suggests our new SAP can act as internal curing agents in concrete. And in this slide, we evaluated internal curing effect of new SAP1 within three different alternative cement mixes, PLC, LC3, and mixed with 70% GZBUS, ground granulated blast furnace slag. And we utilized Japanese raw materials to simulate these mixes due to their availability. And this data indicates even in alternative cement mixes, our new SAP1 can enhance strength effectively. So we believe our new SAPs is effective not only in traditional conventional concrete, but also in alternative cement mixes. In this slide, we evaluated the relationship between GZBS ratio in binder mix and compressive strength. This data indicates by increasing GZBS ratio in binder mix, we can reduce the amount of cement by more than 10% by using our new SAP1. And we successfully conducted a production scale test at the real precast concrete plant, fabricating a slab and U-shape together and using 80% GZBS mix combined with our new SAP1. Now let's turn our attention to the impact of SAP on shrinkage. From our original shrinkage test with two different mix, one with 100% potent cement and another with 70% GZBS. This data shows our new SAP1 can minimize autogenous shrinkage in both mixes. So yeah, previous studies have reported SAP can reduce autogenous shrinkage, and we confirmed our new SAP also have good properties to reduce autogenous shrinkage. On this slide, we focus on the impact of SAP on freeze-thaw resistance. We have confirmed that our new SAPs can significantly improve freeze-thaw resistance compared to control mix without SAP. And these air voids created by SAP act similarly to end-to-end air. Now I'll talk about the potential of our new SAP as admixtures for 3D concrete printing. As I mentioned earlier, our new SAPs have slow absorbing behavior and good properties that enhance concrete properties. On the other hand, 3D concrete printing is one of the promising technology that contribute to good productivity and lower environmental impact. But it requires precise rheological control to ensure good buildability and good physical properties under harsh drying condition. So we believe our new SAPs can serve as innovative admixtures for 3D concrete printing. This slide presents the test result for buildability with mortar mix designed for low carbon concrete. We used new SAP3 as liquid type, expecting its application for two-case system in 3D concrete, which have a secondary mixing process just before extrusion. And we evaluated buildability by measuring yield stress of mortar mix through penetration resistance test. This graph shows the mix with SAP liquid have showed better, improved yield stress behavior compared to without SAP mix. So also a faster study needed, but we believe our new SAP can improve buildability for 3D concrete printing. Finally, I'd like to summarize the key points of my presentation regarding our new SAP. And we believe that our new SAP can play a vital role in improving sustainability of concrete. That's it. Thank you for your attention.